Hello everyone. So welcome to another lecture in game development. So this week's topic is solid principles in game development. So yeah, as you already know, because of the lockdown, we have to conduct the lectures that I usually do in the university as online lectures. So this is the third lecture I'm doing after the lockdown. Alright, so solid principles. So if you haven't heard this before, solid principles are a set of guidelines that is designed to support object oriented design. Now if you are not sure about what object oriented design means, actually that is like a process that we can use in software development to uh, develop or solve some problem in a software, a process or a planning system that we can use using the concept of objects and interactions between those objects. So we consider the modules in software as objects and we solve the problem uh, by thinking of them as interactions between objects. So that's the way we design the software. Alright, so these are the solid principles. Solid is an acronym like which creates this created by these 5 principles taking the first letter, and they were introduced by an American software engineer, Robert C. Martin. Right. So yeah, 5 design principles in object-oriented software development intended to make software designs more understandable, flexible, and maintainable. So the first principle is single responsibility principle, and then open closed principle, and let's go substitution principle, and interface segregation principle, and dependency inversion principle. So let's go through one by one and see what each of those principles stands for. So the first one is single responsibility principle. A class should have only a single responsibility. Changes to only one part of the software's specification should not be able to affect the specification of the class. So yeah, let's try to understand this in context of a game development. So yeah, just like in any other software, game is also a software, so it has classes, components, pretty much same as anything else, any other kind of a program. So here what it says is a class should have only a single responsibility, right? So for example, if we take a Unity project, in Unity we can write scripts. So this is our character. Okay, so we can write a single script for this character, and let's call it the, let's say, player character controller. So within that class we can define the movement of the character, and also how does the camera behave, and also how does the physics of the character works, and also how does the animations are changed, how does the animations work, and we can actually put everything, we can write everything in the same class. And yeah, in fact it will work also. We can make it get it working by including all the functionality into a same class. But the problem is, if I put everything in a single class, then let's say later on we encounter some bug related to, let's say, jumping. And then to fix that bug, you have to modify this character controller class, which contains all the logic of the character. And but because it is in the same class, it will definitely affect other parts of the class as well, which makes it harder for us to maintain the project. Also, if we have to add some, extend some functionalities or add new functionalities, so that is also going to be a little bit harder, because we already have a huge code within that class, and as you make changes there, you may encounter other problems. And also it will make very hard for someone to read that class and understand what's going on, what is the architecture of this project, because if you do it like that, basically that's not much of an architecture. So for example, so what's the better way to do this according to this principle? So we can look at it like this. So instead of using the same class for everything, we can define, like as I have done here. This may not be a perfect example, but this is what I'm trying to do here. We have a player input script which handles all the player input related functions, and also character animation controller script which takes care of character animations, and also character movement script which defines the logic of the movement of the character, and also a main character class which is kind of like the main component that put everything together and keep it running. Okay, now if we take Unreal, so it may not be that clear with blueprints in the beginning, but if you open one blueprint, now you can see here we have this human, this root component, and also we have a mesh, and we have this character movement component. So here this character movement component has everything related to movement of the character. You can see character movement in jumping and how it behaves in falling. Everything is there, right? So, and also in the mesh we can assign a separate class for animations. We call it animation blueprint, and within that animation blueprint we do everything related to animations of this character. So we can see kind of that principle, we can see that principle applied here, because we try to have separate components or modules which is focused on single aspect of the system. Right, now the next principle is open closed principle. Now that means software entities should be open for extension but closed for modification. So in more software specific terms, design and implementation of the code should allow to add new functionalities with minimum changes to the existing code. Now I got a nice picture to explain this. This is from article in Gamma Sutra about s.o.l.i.d principles. So open close principle. Open chest surgery is not needed when putting on a code. So that means well, the modification or the new feature you have to do is put in a code to the character. Now to put that code, you don't have to open the chest of the character and do some stuff and then put on the code. You should not have to do that. You should be able to just put on the code without doing all this work. Well, if we take example in games, okay, let's say in this world there are a bunch of, well, enemy characters like this, and we have already implemented uh, an AI controller class for these enemies, and in that AI controller, let's say we already have a function or an event which allows those characters to move to a given location. Alright, and now let's say we need to add another function to these AI characters. We need to move these characters to a covering position. Maybe in a fight we need them to move to a covering position. So when we implement that, one part of the take cover is obviously find in the nearby cover, and then the other part is move into that selected cover. Alright, so okay, so definitely to extend it we have to newly implement find cover part, but for that move into cover part we can reuse the existing code that we already have to move to a certain position. Let's say move to function. Right now, because of that, because of this new function we need to add, we do not have to make any changes into the existing move to function that we already have in the AI controller. If we have to do something like that, if we have to make some changes in the existing function in order to make the new take cover function work, that means we have something wrong. There is a problem in our design. So what this principle says is we should not have such scenarios. We should be able to implement or add new functions by doing minimum changes to the existing code. Alright, now the next function. Next principle. Let's go substitution principle. So objects in a program should be replaceable with instances of their subtypes without altering the correctness of that program. References to a base class can be replaced by a derived class without any issue. Alright, now let's see this in a game development context. So let's take the same example. We have now now we have a main character, we have an enemy character, right? Now by extending that class we may have created two different types of enemy characters, like different enemy characters. Okay, maybe one of them would be a range attack in enemy, or maybe just with a different character. But anyway, let's say now we have another class that controls the collective behavior of these enemies, like giving commands to these enemy characters. So now that character or that class only knows may not know about the specifics of the child classes. He treats all the enemies as same as the way it treats the main base enemy class. But still, it will be dispatching commands to the child classes of the base enemy class, which are different enemy types. He will be dispatching commands to those classes, those objects, and yeah, just because they at some time they are child classes, that should not make the logic of that enemy controller wrong. So that means whatever the available enemies, they can be the from the base enemy class, so they can be child classes of that class, so which are like different types of enemies. So whatever the available enemy types, that enemy controller should work without any issue. So if I put that explanation into a image, so this is the main enemy type, and these are inherited subclasses of the same enemy, but it has like different weapons or different skills, so like that. And there is a class, another class called enemy controller, which has an array of the currently available enemies, and what it does is it gives commands to these available enemies. Commands can be attack, take cover, fall back, flank, like that. So now this class does not have to know any specifics about these child classes. It will dispatch commands just as it is dispatching commands to this base class, and this system will still work if we have properly implemented this system according to the Liskov substitution principle. Right. The next part is interface segregation principle. Many client-specific interfaces are better than one general-purpose interface. Well, this can also be explained with one of the images that I have from the previous lecture. So in that lecture, we discussed about an example of shooting arrows. So yeah, when we shoot arrows, when an arrow is when any character or any object hit by an arrow, then it should show some kind of a reaction, right? So we had two approaches. So first approach was we define an interface like for the humans, let's say human interface, or just interface called humans, and within that interface we could define a function called on arrow hit, and we could define or implement that function in the main human class, or if we want we can override them here. And then when an arrow hit on that object, we could just call that on arrow hit function. Now if we use that approach, then in order to get to work the arrow hit and reactions on these objects like these grain sacks or explosive barrels, here also we're gonna have to implement the human interface in these objects. But if we do that, the human interface is designed to support or to define some agreement for the humanoid characters, to define some agreement in the system which defines humanoid characters. But if I implement that interface on these objects, it is not consistent because these are not humanoids, and also these it is like kind of having access to the things like walk, jump, that doesn't make any sense on these objects. But if I implement that interface, then that agreement is kind of abused, which is not a good thing. So therefore what I suggested was define a different interface like damageable, and there define the on arrow hit. So this both of these objects and also the humanoids can implement that interface. So this is specific, this is a different interface with a smaller scope. So this is what meant by interface segregation. Many client specific interfaces are better than one general purpose interface. So just like in the previous case, if we go with the human interface, then that's bad. That will break this rule. So by breaking this rule, we will have problems with the maintainability, reusability, and changing the code. Right. The next and the final principle is dependency inversion. One should depend upon abstractions, not concretions. Abstractions should not depend upon the details. Details should not depend upon abstractions. So this is kind of hard to understand when we put into words like this. So basically what it does is decouples software modules. Well, if I take this example, instead of having treating these enemies as in the type of base class, or maybe if we can have some interface like enemy interface, and make this base class implement that that enemy interface, and those enemy interfaces can, and this, when this class is extended by these classes, then they will also have that interface functions. So yeah, either we should use base class reference or interface reference. So anyway, if instead of having the base class reference, if we have the child concrete references, well, instead of interface, if we have concrete references to these classes, then this class and this class is coupled. That means this class has to know about this class, otherwise yeah, well, without coupling we can't have that kind of a behavior. So the problem with that approach is, so let's say we are adding a third type of enemy class which inherit from this base class. So now that type wouldn't work with this enemy controller, because in order to work with this, it needs to have concrete references to these subtypes, and somehow we have to add references to this third subtype also inside this enemy controller. So that means we have to, if we modify a child class here, then we have to modify this enemy controller as well. So that's how we detect dependency between two classes. So yeah, that's not a good sign. So that's how we identify we have violated this principle. So we should avoid such scenarios when we design our systems. Okay, so with that I'd like to conclude this lecture about solid principles in game development, and if you have any doubts or questions or problems regarding these principles or anything that I have shown in this lecture video, please feel free to comment or clarify. And yes, thanks for watching. See you in the next episode. Goodbye.